In a situation where we actually want to characterize relationship between two variables, and if we assume that a linear relationship exists, of course, we're actually going to fit a simple linear regression model. Okay. Now, when we fit a simple linear regression model, of course, in the specification linear regression model, we have the deterministic part of the model, and we have the random part of the model. The deterministic part of the model is actually the explained variation, while the random part of the model is what we call unexplained variation. And the next thing we're actually going to do after specifying our model, we're actually going to estimate parameters. Okay, the one I call the beta naught and the beta 1. And after estimating the parameters in the linear regression model, the next thing we're going to do what we call model validation, which we call model diagnostics. That was what we did last week. Why are we doing model diagnostic? We're doing model diagnostic just to revisit our assumptions, because we made assumptions from the beginning, and we actually want to see whether the assumptions are not violated. You remember what we did last week, where we investigated the assumptions of simple linear regression, uh, you know, linearity, assumptions of linearity. You remember we have assumptions of constant variance, assumptions of normality, and assumptions of independence. And not only that, we also investigate if there is presence of an unusual observation. When I say unusual observation, I could be talking about outlier, or I'm talking about high leverage. Okay. Now, let me tell you this. In a situation where we actually investigate our model for validity and we realize there is violations. Okay, if there is violations, there's something need to be done. And what need to be done before we go into prediction is transformation. Okay, and that is the essence of today, the essence of today's topic. Okay, the essence of today's topic is more or less like a remedy. It's more or less like, okay, when the assumptions are violated in the simple linear regression model, what can we do? Okay, if we have choosing to transform, okay, we can choose to transform our model. Okay, and that is actually going to be our focus today, which I call power transformation. Can you guys confirm if you guys are hearing me clearly?
Yes.
Thank you so much. Thank you for confirming that. Okay, now we want to talk about variable transformation right now. And of course, I've already prepared your mind. You know the reason why we want to transform. I told you, statistics, it's like a story that goes on and on and on and on and on. And there's a reason why we're doing what we're doing today. Uh, excuse me. Okay, now I wanted to take a look at this. I want to consider different kind of function right now. Okay. Now, initially, if I have W and I want to have a linear transformation, okay. Now, there are different kind of transformation around. Okay. Number one, because if you want to transform your model, maybe because there's a problem, okay, there are different kind of transformation around. And number one of them is what we call linear transformation. Now, linear transformation, probably, maybe I have a W before and I multiply W by 2. I double that. Okay. That's a transformation, because 2W is not the same thing as W. And another form of linear transformation I can have around, maybe is to probably add a constant to W. Initially, I had W and I had 1 to that. Take a look at that. 1 plus W is not the same thing as W. Okay, this is an example of a linear transformation. Okay, but let me tell you this, before we can actually apply any type of transformation, that depends on the severity of violations. Okay, that depends on the severity of absorption violations. Okay, what I just show you right now is what we call linear transformation. Now, another transformation we can have around is what we call power transformation. Now, at times, a situation whereby the linearity assumption is violated. You remember I walked you through a data set last week where we plotted a scatter diagram and what we had was a curve. I told you when you are when you before we analyze data, that's what we call data exploratory analysis. What we normally do at the beginning of research, what I call a preliminary investigation, is actually to have a diagrammatical plotting of the response variable against the predictor, so that will enable you to have the sense of the relationship. Okay, now situation whereby probably the assumptions of linearity is violated. If the assumptions of linearity is violated, of course you could have a transformation. Initially, if your variable is W, you can actually square that. Why do you need to square that? Maybe you are actually suspecting a curve, okay, a quadratic curve. Okay, and of course you can actually raise that to power 3. We have different kind of function in mathematics. You have quadratic function, the cubic, and so on like that. So but I want to tell you all of that actually fall under power transformation. Okay, now the next thing that I'm actually want to talk about, we have other transformation. We have situation where power transformation may not work, but what is actually going to work may be other transformations such as this. Take a look at that. Maybe initially I got a W and I needed to find a sign of that, the sign of that. Okay, so when I find a sign of W, I'm no longer having W. It means I have a new set of data in place. Okay, and you know what, at times we could have situation where we have W1, W2, and of course the transformation that we actually going to make could be the ratio of the two, because the ratio of W1 to W2 is actually going to give you a different data set that is different from W1 and W2. So what I'm trying to show you right now, I'm trying to show you different kind of transformation that we can have around. And of course we can talk about transformation when there is a problem of absorption violation. Okay, how do we transform our model if we still want to use linear regression? Okay, how do we transform our model? And of course, what I'm walking you through right now is different kind of transformation we can have around. Okay, now I I want to go into power transformation right now because we use power transformation a lot. Okay, now I want to generalize the power transformation. The other time I'm talking about this. Okay, we could have W raised to power 2, W raised to power 3. It could even be W raised to power 4, power 5, and so on like that. That's what we call polynomial. You get what I mean? Okay, polynomial of degree 1, polynomial of degree 2, polynomial of degree 3, and so on like that. Okay, now take a look at that. I'm actually going to have a generalization right now. Take a look at this guy here. Okay, let's say initially I have a W, but you know what, W has a problem. And because of the fact that the model with W has a problem, the variable that I have has a problem, maybe probably with absorption violation or probably with the presence of unusual observation, okay, I'm actually going to have consider a power transformation, W raised to power lambda. Okay, lambda is not equal to 0, lambda is not equal to 0 means lambda can be 1, lambda can be 2, lambda can even be a fraction. Okay, now take a look at that. And we can also have another example of power transformation where we're going to log, okay, where we needed to find the log of the W, okay, finding the log of the W, maybe, we're actually going to give us a different data set, okay, in a way, logging, introducing a log to variable could actually make us to improve on the model. Only that whether you're going to apply you know this guy here or this guy here actually depends on the severity. Oh my God, it depends on the severity of the violations that we talk about. Okay, it depends on the severity of the violations that we talk about. And of course, I'm actually going to walk you through that now. Okay, you're going to see that. Oh my God, take a look at what I have here. I actually want to explain different kind of shapes that we can have in this world. Take a look at this, different kind of transformation. Now, if I have a W, okay, I told you the initial variable, the original variable is W. And you know what? W has a problem with absorption violation, okay? And you know what? When W equal to, I'm going to show you something now. Take a look at, I'm going to show you something now, okay? I'm going to show you something now. When lambda equal to 0, I want you to pay attention to the green line. Pay attention to the green line. When lambda equal to 0 right now, when lambda equal to 0, it means I'm talking about log. I'm logging. Look at that. When lambda equal to 0, it means if I want to transform my variable by taking the log transformation, I'm going to say that again. If I want to if I want to log, if I take the log of my variable, okay, when I plot that, I'm actually going to have the shape that you're seeing, the green line. Take a look at the green line right here. I'm talking about this guy right here. Okay, that is what you're actually going to see. Okay, but you know what? When lambda equal to 1, of course, when lambda equal to 1, there's no transformation. You know that? When lambda equal to 1, what do you have? You still have your W. Okay, when lambda equal to 1, what do you expect? Are you surprised with what you see? Of course you expect a straight line because there is no violation. Okay, when lambda equal to 1, I don't need any transformation. My model is fine. The linear relationship is already established. Oh, can you guys confirm if you guys are hearing me clearly?
I can see and hear you.
Okay, thank you so much. Okay, I also want another person to confirm if you're hearing me. Is everybody hearing me? Everybody? Are you guys
Yeah.
hearing me?
Yeah.
Oh, thank you
Yeah.
so much. Thank you so much.
Yes.
If you're not enjoying my party, oh my God, let me know. This is another party, okay? We're gonna have a fun here. Now, what I'm trying to talk about when lambda equal to 1, take a look at that. When lambda equal to 1, W is going to be equal to W. It means I don't need transformation. Okay, if lambda equal to 1, I don't need transformation at all. That's a straight line. Of course, you know how to figure that out. I walked you through this last week, just during the regression diagnostics, where you have a way to test for linearity absorption. I remember I used a scatter diagram and I used a residual plot. You remember that? In that situation, if the art absorption is not violated, of course, you don't need transformation. Okay, so which means lambda equal to 1. Okay, I want you to take note when lambda equal to 2. Okay, when lambda equal to 2, it means I have a quadratic. Okay, that's going to be a curve. Look at this guy here, lambda equal to 2. Okay, it means I'm having W raised to power 2. Okay, so that is going to be the curve. That's going to be the shape you're actually going to see. And you know what? When lambda equal to half, okay, at times when lambda equal to half, we have what we call a square root transformation. When lambda equal to half is actually this guy here, okay? Equal to half means lambda equal to 0.5, okay? That is going to be the curve. And when lambda equal to -1, okay, that is what you're going to see when lambda equal to -1. Okay, so what I just show you right now, I actually show you different kind of shapes, okay? But you know what? You know what? The kind of transformation that you need actually depends on the kind of shape that you see in your data. I told you what you're actually going to start with. You need to first start with a scatter plot. Okay, if you want to know, if you want to have the sense of the relationship, okay, if you want to have the sense of the relationship, you need to first plot the response against the predictor And let me tell you this, any of this shape will emerge. Any of the shape that I'm showing you right now will emerge. Okay, if this shape emerge, for instance, if this guy emerge, it means you cannot fit linear regression model. It means you got to fit a polynomial regression model, okay, with degree 2. You're going to fit polynomial of degree 2. Of course, you know, linear regression model is a polynomial regression model of degree 1. I'm going to say that again. Linear regression model is a polynomial, it's a class of polynomial regression model of degree 1. Of course, you know, linear relationship is a polynomial of degree 1. Okay, now, so if I wanted to take note of the shapes that I have here, because when you do a scatter plot, the shape that you see in the scatter plot, okay, it's actually going to match with any of this shape right here. If it match with any of this shape right here, and that will give you the sense of the model you're actually going to fit. Because you know why? We have model that have different shape, and we have data that also have different shape. If you actually want your model to extract the largest amount of information in the data, then you're actually going to use the state of the model and the state of the data have to be the same. Okay, if the data structure is linear, okay, you have to use a linear model. That's what I'm trying to say. If your data structure is quadratic, then you have to use a quadratic model. If your data structure is cubic, then you have to use a cubic model. Okay, so the state of the model and the state of the data must match. In a situation where there is no agreement between the state of data and the state of the model, of course that research will be misleading. Okay, and that is why I'm trying to show you different kind of shapes that we can have. Before we go into research at all, we have this kind of shape in place for model. Okay, and when you go into research, you actually need to investigate your data. Okay, you need to understand your data. You need to do data exploratory analysis, okay, which I call the preliminary investigation. For you to, you now need to compare the shape that you see with the shape right here. Okay, in a situation where the shape is linear, and it means lambda equal to 1, then it means you don't need any transformation at all. But in a situation where it is not, of course, transformation is needed. Okay, now the next thing now, why transforming variables? Why are we transforming variables? Okay, we are transforming variables just because a variable is given in the data set doesn't mean it's appropriate. I'm going to say that again. Variable may not be appropriate, and that need to be transformed. Okay, because if you analyze inappropriate variable, I'm going to say that again. If you analyze inappropriate variable, there's going to be a problem, and that is the reason why we need to investigate. Okay, so when it is inappropriate, then you got to analyze. Now I'm going to give you an example right now. Take a look at what I have now. The study of a country's economy development on child mortality rates. Okay, now if you're carrying out a study of a country's economy development, right now I have released practical assignment guide, like practical 1, where I need you to tell me what you want to work on. That's practical 1. Practical 2, you're actually going to take your data. Okay, you need to collect your data. That's practical 2. Then practical 3, then you're going to do analysis, okay, where you're going to get your result. I'm still going to release a guide on practical 3. But you know what? Practical 1, you need to tell me, okay, all what I need from you, okay, is just, okay, the topic you want to work on. Okay, and you know what? You can work in group, and you can decide to work alone. If you want to work in group, the maximum number of people that I can actually tolerate in a group is going to be 3, maximum. 3 people in a group. There can be 2 people in a group or 3 people in a group, and you can also decide to work alone. There's a problem. Okay. Now, I want you to be paying attention to what we're doing right now. Okay. This may be what you want to study. Take a look at this example the study of a country economic development on child mortality rates. Okay, now what is going to be the variable? Of course, the variables of interest is going to be child mortality rate, the GDP, and the population. Those are the variables. Okay, if I want to carry out that study. Okay, now I wanted to take a look at this. Consider model. If I want to talk about child mortality rate, okay, the child mortality rate is just going to be GDP divided by population. What am I doing here? This is, I'm dividing. It means I cannot use GDP alone. I cannot use population alone, but I need to transform them. I will quickly take you back. Oh my God, you're going to see something right now. Give me 1 second. Oh, it is right here. This is what we're doing. That is order transformation. W1 divided by W2. That's what we're trying to do. That's what we're trying to apply. Okay? Take a look at that. That's exactly what we're doing right now. Let me tell you this. It is not as if there's a violation right now, but you know what? One of the reasons why we transform, because there's more than one reason why we're going to transform our model. And one of the reasons why we transform is when we have inappropriate variable. Okay, and take a look at the example that I cited right now. Oh my God, I'm enjoying this party. I don't know whether you guys are enjoying the party the way I'm enjoying it right now. Take a look at this guy. I want to get child mortality rate. Okay, the child mortality rate is equivalent to GDP divided by population. Of course, the GDP divided by population is not going to be the same thing as GDP. It's not going to be the same thing as population. Is something else entirely, which we call the child mortality rate. Okay, so which means then another reason why, so like I said, what we're working on right now, why are we transforming the variable? Number one reason why we are transforming the variable is to put inappropriate variable in appropriate manner. Okay, and in this example right now, we don't just work on GDP and population, but you know what? The child mortality that we want to get, it is a ratio of the GDP to the population. Now, the second reason why we do transformation is when we're trying to fix assumption violation in linear regression. Okay, this is one of the major reasons. Okay, so what I'm trying to tell you now, there are two reasons why we transform variable. Okay, to put the variable in an appropriate form and to fix assumption violations. Okay, and you remember last week I walked you through regression diagnostics where we are trying to investigate assumptions violation. And the question we actually want to ask ourselves, the simplest form of any model is linear. I'm going to say that again. Okay, the simplest form of any model is linear. And if you want to start, okay, if you know there's a violations of linearity assumption, and this is what I'm actually gonna do, I need to ask myself what kind of transformation is going to work. Is it going to be linear transformation? Is it going to be power transformation? Is it going to be other form of transformation? Okay, in research we do a lot. We don't Research cannot be rushed. Okay, we do a lot. Okay, so we need to be able to figure out what kind of transformation is going to work. Okay, does linear transformation going to work? That was what I has a question right here. Does linear transformation help? Okay, if it doesn't help, how do I know a particular transformation help? Okay, I'm also going to walk you through that. Oh my God, we want to go into an example right now. And this example, modeling salary from years of experience for professional workers. Okay, you guys confirm if you guys are seeing the example right now?
I see it.
Okay, thank you so much. Thank you so much. Okay, now take a look at this. I want to look at the effect of experience on salary. And I started by having a scattered diagram. I told you this is what you'll do. This is what we call preliminary investigation. What are you trying to do right here? You're trying to plot the two variable because you actually want to know the kind of shape And what are you seeing right now? Oh my God, I'm seeing a curve that is looking like a curve. Okay, that is looking like a curve. Take a look at that. That is looking like a curve right now. Okay, now if that is looking at a curve, now the question now is, what is making this to look like a curve? What if we do a linear transformation on experience? Okay, because maybe probably the experience that we use right here is inappropriate. Okay, maybe the experience that we have here is inappropriate. Don't forget. Okay, one of the reasons why we do transformation is maybe we have inappropriate variable. Okay, now what if we do linear transformation on experience? Oh my God, instead of considering experience, we consider work history index. Okay, work history index is experience minus 1 divided by 40. I want you to take note of that. Take a look at that. Work history index is more appropriate than using experience. And what have we done to experience right now? We transformed experience, okay, to get a new variable called work history index, which is experience minus 1 divided by 40. Take a look at that. Okay, now when we do that, we want to have another scatter diagram right now. Take a look at what I have right now using salary on work history index. Okay, now you can see that when I use the work history index instead of using experience, I still have a curve. Look at that. I still have a curve. Okay, take a look at that. I still have a curve. But why am I doing this? I'm going to show you something right now. Now, you're going to see something right now. If you take a look at what I have right now, where I'm using the the work history, if you take a look at it too, I still have the same relationship, but you know what? I'm still going to tell you the reason why the work history index is more appropriate than just using experience. Okay, I'm going to walk you through another example right now that you're actually going to like, where we want to predict the brain weight based on the body weight of mammals. I'm going to say that again. We want to see whether using the body weight of mammals, can we actually predict the brain weight? Does the brain actually, is it proportional to the body weight? That is what we want to figure out. And take a look at what we have right here. We're using we're using elephants. Okay, we're using the body weight. We're looking at the relationship between the body weight of elephants and the brain weight. Okay, take a look at this. That is the brain weight. Okay, and that is somebody said, I think I saw the chart right now. Somebody is asking me to explain why. He said, wait, can you explain why work in this index was helpful if data was still non-linear? Why didn't you transform? Yeah, let me tell you this. Um, that's a very good question. I want to tell you something right now. You know, uh, I asked a question. What if we do a linear transformation as experience? Linear transformation on experience will not lead us based on what we have here, since we're still retaining our curve. Linear transformation experience it's not going to work. Okay, but in terms of appropriateness, in terms of you know uh economically, work history index is more useful than experience. Okay, but you know what, in terms of linearity, it doesn't work. And based on what I'm seeing now, of course the quadratic is actually going to work. Okay, quadratic transformation is going to work. Okay, I just take a pause on this right now. I'm still coming back to that because of my time. Okay, so you have asked a very good question. Okay, linear transformation does not work. Quadratic transformation is what's going to work. Okay, now take a look at what I'm doing right now. I have a lot of elephants, Asian elephants, African elephants, and so on like that. Okay, and uh, I fitted a straight line model. This is what I have. Okay, the beta naught is 71.2, and then the beta 1 is 0.97. Okay, this is a model. We can actually use this model to predict the brain weight of elephants, of any given elephant, given the body weight. But you know what? I want you to take note of this. Take a look at that. That is based on what you learned last week. Okay? Look at that. Based on what you learned last week, this guy and this guy is looking like an outlier. Do you remember what you learned last week? Look at every other one right here and look at this particular point. The African elephant and the Asian elephant, they weigh more. They looking like an that is looking like an outlier. Okay. Now I want to show you something right now. When we try to remove these two elephants from the study, okay, what are we going to have? I want you to take note of something right now. When you decide to remove the two elephants and you plot again, okay, we're actually going to have something like this. Look at that. We are, if you know, that is removing the two elephants. Okay, that's what you're going to have. But there's something I want to tell you right now. Using the residual plots. I walked you through a residual plot last week, and I actually wanted to see the difference between uh, the two. Now, this is a residual plot, okay, for the elephant. When we're looking at the effect of brain weight on the body weight, okay, I want you to take note uh, of that. And this guy here is a normal QQ plot. You remember I told you last week that um, we use a normal QQ plot to test if normality assumption is violated, and we use residual plots to investigate if linearity or the assumptions of constant variance is violated. Okay, I want to take note of what I'm trying to show you uh, right now. Okay, now the if you take a look at the diagnostics that we did right here, what can you see? We know I told you uh, for linearity assumption not to be violated, we don't expect a pattern, right? I think I told you. Do you remember that I told you that for linearity assumption not to be violated, residual plots shouldn't show a pattern. But right now, take a look at that. This is showing a pattern. And take a look at the normal KQ plot. We don't expect the normal KQ plot to be like a flat, like this. We expect something like a straight line in a normal KQ plot. Okay, so which means with the two elephants, with the Asian elephants and the African elephant, there is a violation of absorption. Okay, there's a violation of absorption. There's a violation of linearity absorption right now. There's a violation of normality absorption right now. And I can also assure you that if you carry out a Cook distance on outlier, there's possibility that could be violation as well. But you know what? Transformation is actually, we can use transformation, to bring situation back to normality. Okay, now take a look at this. We now want to consider four different transformations. We know there's a problem. Okay, right now, take a look at this. There's a problem here. Residual plot is showing a pattern. I told you, residual plots shouldn't show a pattern for assumptions of linearity to hold. And assumptions of normality is violated right here because we actually expect a kind of a diagonal straight line. But what we have right now is not a diagonal straight line. Because of that, the assumptions for normality is actually violated. Okay, now what are we going to do? Now we want to consider different kind of transformation. Take a look at this right now. We want to consider different types of transformation. And what are we going to transform? Okay. We want to take a look at this guy here. Um, we want to transform the two variables, the brain weight and the body weight. What are we going to do? We can define a new variable called 1 divided by brain weight. This is a new variable. And 1 divided by body weight, that's another new variable that we plot. Okay. And when we plot, we're going to take note of that. Then Another transformation that we can do the log of the first one and the log of the second one. Take a look at that. Another kind of transformation that we can do is to do a quadratic transformation, where we find the square root of the two variables. Uh, uh, okay, where we find the cube root of the two variables. Okay, and look at the transformation right here as well. Okay, now I want to award an extra credit right now. Can somebody tell me which transformation actually, as attain the linearity? Can somebody tell me, out of the A, B, C, and D, which of the transformation attain linearity? Oh my God, somebody said B. That is a correct answer. Now you're going to send a message to me for extra credit. If you take a look at B right now, look at that. That is looking like a straight line. It means after transforming, what has worked right here is a log transformation. And let me argue this with you critically. The reason why the log transformation actually work, because the Asian elephant and the African elephant are heavily weight. They have extreme values. Okay, when they have extreme value, the probability distribution of the data will be skewed to the right, will be more skewed to the right. And what can we do to bring situation back to the center? Take a look at this. You saw a shape of a normal distribution before. Okay, if you chop this shape for this time around, it's gonna look like that. Okay, because the two elephants are so heavy compared to other elephant. Therefore, they're going to induce what I call a positive skewness. And what are we going to do? It means what we're going to do is we're actually looking for this. We're looking for a normal shape. We want to bring things back to the center. Then we believe that if figures are too high, okay, we will take the log of figures that are too high. It's actually going to compress, is it not? If I take, what is the log of 100? The log of 100 is going to be very small. The log of 1000 is going to be very small. Okay, what I just work out with you now is just critically, okay, what we do. We could do a log transformation. If you actually want to solve problem with positive skewness, we can also do a square root transformation. Whether square root transformation, whether log transformation, is actually you are trying to apply that to data set that are skewed to the right. Okay, now the log transformation actually work right here. Okay, so why do I use the same transformation on X and Y? That's another question. That is, I log Y, I also log X, because the two of them have to do with weight. We're talking about brain weight. We're talking about body weight. They got the same unit. How can you guys confirm if you guys are hearing me clearly?
We can hear you.
Okay, because at time we could use a log, we could log one variable, we may not log the other one, but right now we're logging the two variables because the two variables are weight. We're looking at the effect of the brain weight on the body weight. Take a look at that.
I have a question.
Okay, go ahead.
For number C, I can't really see what square root it is. The pixel is kind of broken. I can't really see what number is.
Oh, oh, you mean this guy here, right?
Yeah, the square root of
Oh, that is
number
3. That's just cubic. Oh, cube root.
a cube. Okay, thank you.
Yeah, but this one is square root, the one in D.
Yeah, okay.
Okay. Now,
I have a question as well. I'm
go
sorry.
ahead. Go ahead.
Let's just say that the Asian elephant and African elephant, let's just say they were like extremely low values and the data was skewed to the left. What kind of transformation would we use then?
Oh my goodness, good job. That's a very good question. If I hear you correctly, let's say we have elephant that have extremely low values. Now, if we have elephant that have extremely low values, it means the skewness is going to be to the left. And if the skewness is to the left, you're going to have something like this. I'm going to show you now. Can you see that? It's skewed to the left. And when it is skewed to the left, of course, the transformation that we work here, it could be a square transformation. It could be a cube transformation. I mean, something raised to power 2 or something raised to power 3. Why are you raising something to whole number? You are raising something to whole number because you believe the number is too small. You want to make it big. Does that make sense to you right now?
Yes.
Okay. And the one we're considering right now, because the African elephant and Asian elephant, they got a very big value. They have extremely high value. They're actually going to, induce positive skewness. And of course, if you want to bring some, that back to the center, of course, what you're actually going to do, you're going to compress. And of course, in compressing data, we're going to use a law. We can use a cubic transformation. We can use a square root transformation. But you can see this guy is also very close. Okay. That one is also very close, but the better one, oh my God, the best one is the B. Okay, take a look at that. And that was why, if you really want to know the kind of transformation that work, of course, we're going to do try by and error. Okay, we're going to try different kind of transformation, and we're actually going to check ourselves. And that was why I said which transformation we choose. Okay, of course, I call that advertisement time. Of course, you've already chosen that. Now, let us now look at the residual analysis. Before, this is a residual before, okay, before removing the African elephants and the Asian elephant, the residual show a pattern. Take a look at that. Now, after removing that, oh my God, take a look at what I have right now. After removing that, okay, after doing transformation, we did not remove. Let me tell you this. We did not remove, we transform. Let me say that again. Why is it that we didn't remove the African elephant? I told you the other time. We don't just remove outlier. The only way the only condition for you to remove outlier is when you have an error, like you have a recording error. Okay, but African elephant, Asian elephant exist. They are genuine observation. Okay, we need to, the only thing we actually gonna do is to transform our model. I want to tell you, they are still part of this data, only that will transform. Now, take a look at this right now. After transforming, take a look at that. After transforming, we're going to run our regression again. Okay, we're going to run that regression. It's going to be log of brain weight on the log of body weight. And look at our residual now. Oh my God, our residual is good right now. It's without pattern. So that, to me, the transformation has really worked. Okay, so what I'm showing you right now. Now, if you want to know the code in R, this is the code. Okay, this is the code. Okay, if you have a data set on brain weight, you have a data set on body weight. Okay, if you write that in now, you're actually going to have this. And of course, if you want to have access to plot, okay, you're going to write plot mode 2, 1. That is going to give you the residual plot. And that is actually going to give you the residual plot before transformation and after transformation. Now, what about the normality absorption? Before transformation, look at that. That is a normal KQ plot. I told you there was a violation. Look at it. Look at that. But after transformation, oh my God, look at what I have right now. After transformation, I told you we should have a diagonal straight line. So which means the transformation that we have done has really solved a lot of problems. Number one, it solved the problem of linearity. Number two, it solved the problem of normality. Take a look at what I'm showing you right now. Take a look at that. And of course, if you want to have access to this, if you want to have the code in R, this is actually the code. You're going to write it after, you're going to write plot into mode 2. Okay, plot into mode 2 will give you the normality plot, and plot into mode 2.1 will give you the residual plot. Take a look at that now. Everything is fine. Now, when you want to look at the normality and you look at the linearity, okay, take note of that. So why does lot transformation work? I think I've already told you, okay, how it works. And if you want to look at that mathematically, this is the origin of the formula. Brain weight equal to alpha multiplied by body weight raised to power beta 1 multiplied by delta. Okay, when you take the log of both sides, it means initially, linear relationship does not exist between the brain weight and the body weight, but this is mathematical. This is it is the relationship is multiplicative. That is, and when you have a multiplicative relationship, you're actually going to take the log of both sides. Okay, when you take the log of both sides, take a look at that. It's going to be log of alpha plus the log of that plus the log of that. Take a look at what we have now. What does it lead to? Oh my God, this lead to log linear regression. This is what we call double log. Okay, this is what we call double log regression model. Okay, where we log the two variables. Okay, take a look at that. We log the two variables. Take a look at that. Okay, what if you don't know what the model is supposed to be like? Okay, in the future lectures, general process for variable transformation will actually be discussed. Okay. Um, Oh, my time is up. My time is up. I gotta go right now. I'm actually gonna let me see what I have left. Let me see. Oh, that is the end of that. Okay, let me quickly do. I'm sorry, I'm gonna take 2 minutes of your time because this is the last page. Okay, now what have we done today? I've introduced you to power transformation. Okay, and the power transformation is very useful. Okay, very useful to obtain linearity, to stabilize unequal variance, to obtain normality, to get rid of unusual observations. Okay, but you know what? But not guaranteed to fix the problems. Okay, not guaranteed to fix the problem. Also, what if your variable values are negative? Okay, because if your variables values are negative, can you find a log of negative? That's going to be error. Can you, if you raise negative raised to power something, can you find the square root of a negative? Okay, so situation and temperature values, they could be negative. For right now, maybe we're having, yesterday we had a negative for 10, okay, 10 degree. Okay, now take a look at that. So that is going to be the end of my lecture today, power transformation. Is there anyone want to ask question before I go away today? Is there anyone? Okay, I want to appreciate everyone who have attended my lecture today. I hope you guys enjoyed the practical party. In case you need more clarification on what I've done today, of course, you can actually reach out to me tomorrow during my office hour for clarification. Okay. Until on Wednesday that I'm actually going to come your way again. Make sure you stay safe and have a good day, guys. Bye for now, guys.
Thank you
Thank
very much.
you.
You
Thank you.
welcome.
Thank
You
you.
welcome. You welcome.
Oh, I had a
Okay.
question about the practical assignment actually. So on Sunday, like this Sunday night is like just our idea that's due, right?
Yeah, the practical assignment, practical one, is you only need to share the topic that you want to work on. Okay, and you know what? I've put a deadline for submission of the practical one. Let me also tell you, you can work in group. You can work with 2 people or 3 people. The maximum number of people in a group is 3, and you can also decide to work alone. Okay, you can decide to work alone. Okay, like I said, you
Okay.
can. So does that make sense? Have I answered your question?
Yeah. Well, then is there like a rubric for it, or we just write like a couple sentence explaining like what we plan to do it on?
Yeah, there's a rubric for it. I think I put it. Did you see the practical assignment guide that I published on the module?
Maybe. Let me check.
Yeah, you need to check, because in that I asked you to specify the variables that you actually want to work with, and stuff like that. So you can check the practical assignment guide on the module.
Okay.
Okay.
Okay. Thank you.
Have I answered your question now?
Yeah, thank you.
Okay,
And
you're
I guess
welcome.
I also, so it says on there like that you have to, like your topic has to be gathering data in your course of study, like what we're majoring in. Does it actually have to be, or can it just be like anything? Because like if I work with someone, they won't necessarily have the same major as I have.
That's fantastic. I think what you're trying to say now is that if you work with someone, there's possibility that you guys may not be majoring in the same. Okay, I think I'm flexible. You can decide to work in the area you are majoring in, or you can also decide to work in any area. Does that make sense?
Yeah, that makes sense. Thank you.
Okay. So bye for now, guys.